everyone. My name is Samrachana, and I'll be teaching probability, introduction to probability today. So I'll cover half, two-thirds of this course, and Suresar will take over at some point. Also, just to give you an idea of the class today, we'll be doing some lectures, but there will also be a lot of problem sets and actual working with pen and paper. So we really encourage you to start having that, and then start talking people around you, because this will be a group exercise. We'll have volunteers walk around the room to help you. But once I finish with the first half, we'll start with problem sets 1. So we use probability quite a lot in our daily life. We talk about things like chance, likelihood. Whenever there is no certainty, probability comes very handy. When we talk about machine learning or statistics, the whole idea is to quantify uncertainty in an experiment. So we are very interested in quantifying outcomes when those outcomes are not certain. Some might be more likely than others, and we need an idea or tools to quantify that. So that's what probability helps us with. In this course and in the rest of the lecture, we'll use probability to typically represent relative frequency of outcomes. So if you were to do same thing again and again and again and again in an experiment, what is the most likely outcome? And can we quantify that likelihood? How often are you getting that? So that is the whole idea of probability, or basis of probability for this course, and a lot of tools you'll learn later. And as I mentioned earlier, so probability is used to understand, or I haven't mentioned it, but I'll talk about it now. We'll use it as a tool to help us understand patterns in nature, so that are real, and also to quantify things that just happen by chance. And it also helps us make inference from a finite sample to make inference on a bigger population, because we can go around and get data for everything in the world. So what we do is we collect sample, and when we collect sample, we want to understand how likely or how much that sample represents the entire population. So probability is a very handy and useful tool to understand and make that inference. So I'll start with a few motivating examples, and we'll work through these examples throughout this course today. A very simple example is a coin flip. We talk about head or tail. There are two likely outcomes when you flip a coin. So if you were to flip a coin for 5 times and record number of heads, and you repeat this experiment 100 times, you might get 2 heads in a row, and that's it. You could get 3 heads, or you could get 5, all 5 heads in a row. And then so on for all these 100 experiments, right? Then we want to ask, like, how can I summarize the number of heads in 5 coin flips through this experiment? So we want to have a number to summarize this whole thing. Also, if I were to repeat this experiment again and again, what is the expected number of heads? So it depends on a lot of things. How likely is the head versus tail? Are they both likely? Is this coin fair, which is what we call to represent both equally likely outcome? And then also, we could also ask questions like, what is the probability of getting 2 heads in a row when flipping a coin for 5 times? So there's so many possibilities, but if I was only interested in getting 2 heads, one after another, in flipping coin 5 times, how can we quantify that? The other example, which we will again talk a lot in this lecture, is about cards. So if I were to draw cards from 52 deck card, and first I draw 1 card, and then again, without putting it back, I draw another card. What is the probability of getting a queen in the first draw? And what is the probability of getting a diamond in the second draw? So for the first draw, we have 52 cards, and we're drawing 1. So how likely is getting a queen? then you need to know how many queens there are, how many cards there are, right? If I were to draw again a second card without putting it back, then the probability is changing. So how can we quantify that? We can ask similar questions if we were to roll a dice. When you roll a dice, you can get 1, you can get 2, 3, up to 6. So when I roll a dice, what is the probability of getting even numbered face versus odd numbered face? And there is one more concrete example that I want to talk about, and we'll go through solving all of these later in the course. So after today's lecture, I expect or I hope you'll be able to answer these questions very easily. So the last question as a motivating example here is about prevalence of diabetes among men. So if we know that in Nepal, 25% of men have diabetes. So these are numbers I made up. It's not really real, but it can be useful. And if I was interested in studying this population in Banepa, so there are 100,000 men in that city. And I know, total number of men. I know the total population of the city. So if I meet a random person with diabetes, what is the probability that person is a man? So there are so many parts, right? There is a probability of getting a diabetes. There is probability of, a person or proportion of men in that city. And then we are talking about this idea of conditional probability again. So all of these ideas will be explored in our lecture. And we'll try to answer some of them. So today's lecture, we will split it into 3 different parts. The first part will talk about all these basics concepts in probability. So we'll talk about probabilistic space, the laws of probability, what it actually means, mathematical formulation, and then we'll talk about conditional probability, the theorems of probability, and independence. And then we'll take a break, we'll solve some questions, some of the things I talked about earlier and more, and then we'll start talking about concepts that will be used throughout the lecture as random variable distribution, and then how we can transfer the concepts we studied in the first part to the second and third part. So to mathematically define a probability, we need this idea of sample space and a probability law. The sample space is the set of all outcomes from an experiment. So for example, if we were to roll a dice, what is our sample space? We get 1, 2, 3, 4, 5, or 6. Those are the only possibilities, right? And then if I were to compute probability of getting an even numbered face when rolling a dice, then I want to compute P of A, and the probability law is the law or the function I use to assign this number to a set of possible outcomes. So there are 3 important concepts here: the sample space that contains everything that you get from an experiment. And then there is something called event of interest. So those are, when I think about even face dice, then it's 2, 4, or 6. And then we want to assign this probability to that event, so P of A. How do we talk about that? Conceptually or philosophically, there are 2 different ideas of probability. One is based on frequency, so you keep on doing the experiment, and then you want to compute how likely that thing is based on the experiment. So what is the most likely outcome based on the number of outcomes you saw and the number of experiments you do. Or if you, in the other way, it's also about encoding your knowledge or belief about the event. If I already knew what is likely to happen, then my probability for that even later can be encoded using that belief. So that is more, it's less concrete than frequency because now we're talking about what we know and what we think should be in the probability function. So okay, is this clear? So the same thing, what I just talked about earlier, if we were to see this in set representation, then omega or W is the outcome space, all possible events for that outcome set of outcomes. And then A is the event we're interested in. So A always falls within omega. There is a bigger world with everything possible, and then the smaller set. And assuming the events we're talking about is finite and countable. So for example, when you roll a dice, it's finite, right? You can count it. There's 1, 2, 3, 4, 5, 6. Then we can think about computing probability as the ratio of cardinality. So cardinality of a set is the number of elements contained in that set. So for here, P of A will be size of A over size of W. So let's go through some more examples here. The first example I'll talk about is drawing cards from a pack of 52 decks. If I were interested in drawing an ace from a pack of 52 deck of cards, then my sample space now is all possible draws. So it starts from ace of heart to 13, or king of heart, and then ace of spade to king of spade, ace of club to king of club, and then ace of, what's the last one? Diamond to king of diamond. So these are, again, they're finite and they're countable. And the event I'm interested is in ace. So how many events there are? 4. So how will I compute P of E? P of getting an ace. Right, very good. We can also talk about getting 2 spades from a pack of 52 deck of cards. So now the possibilities for this event are larger, right? There could be ace of spade and 2 of spade, ace of spade and 3 of spade, and so on. So you'll have a bigger set for this event. And you can also just represent that in a functional form, x of spade and y of spade, where x ranges from 1 to king, and y ranges from 1 to king. And then we can use similar ideas to count the size of the event. We know the size of the sample size, and we can compute probability. This is another example that I've been talking about. So here we're interested in getting probability or an even number when we roll a dice. Our sample size is finite and countable, so 1 to 6. And then even number from these possible outcomes are 2 is an even number, 4 is an even number, 6 is an even number. So we can compute probability of getting the even number when rolling a dice. We're making one assumption when we're computing this. We're making an assumption that each event is equally likely. So when we roll a dice, we're making an assumption that each face is equally likely. But if it was a biased dice or something and one face was more likely than other, then we have to account for that. Then we'll again use probability. Then we need to know how much likely something is versus others. And we'll work through that example later in the problem set. So to formalize this idea of probability, we'll go through some of the axioms or theories that a rule that defines what a probability is. Probability always has to be 0 or greater than 0. So probability of 0 means it's a very unlikely event. Probability of 1 means it's very likely. So the probability of the sample space omega is always 1 because everything you wanted to study within that experiment is within that set. And there is another important law of probability, which is additivity. So if we're talking about disjoint events, two sets with nothing in common, then the probability of A union B is just the sum of A and B. And if you had more partition of the sample space with different A1 to AN, then we can just write probability of the union again as sum. But being disjoint is the key idea here, where the sets don't overlap. So from one event, we can start talking about probability of more than one event. They could be joint, they could be conditional. So here, if we're interested in two events A and B, and we had some idea about event B, then what is the probability of event A conditional on B? And there is a law or rule that defines probability of A conditional B is the ratio of A and B. So if we knew how likely, what is the probability of both of them happening together, and then probability of just the B, then we can talk about probability of A conditional on B. So again, if we're talking about discrete events like 1, 2, 3, 4, 5, 6, and if we, in the example of dice, there could be the probability of A is even numbered face, and then B is just probability of getting a 2, then A and B would be, they overlap in 2, right? So that's A and B is just P of B. So number of times both A and B are in the same sample or same set, which in the example of dice I just told you is just 1, and then number of event B. So from conditional probability, we can also start talking about independence. So if there are two events, A and B, and knowing B is not adding any information to knowing the probability of A, then we can say that A is independent of B, which means A conditional on B is just P of A. So the knowledge of B is not adding anything to our knowledge of A in this example here. And then we can say A is independent of B. We just talked about conditional independence. So by the definition of conditional independent and moving things around, we can write P of A and B together. A intersection B is a product of probability of B and this conditional probability. So if A and B were independent, then we get probability of A and B as a product of probability of event A and probability of event B. And this is a very useful formula in probability theory and later when we start talking about random variables, because if we knew two events are independent, then we can very easily get the probability of them being together just by knowing this marginal probability. And so if A is independent of B, then B is also independent of A. So we can just say they are both independent events. Is there any question up to now? So in that case, we'll go back to examples and try to compute some of the conditional and joint probability. So we'll go back to this example of drawing from a 52-deck card. And this example is we draw one card from the deck, and then we'll again draw another card without replacing the first one. So let A be the event that you get an ace, and H be the event that you get a heart. Can you show A and H are independent? So let's talk through this. If we were to show two events are independent, what are the first few things we need to start thinking about? Intersection, yeah. And then? Marginal. So marginal means P of A, and we'll compute P of H, and then we'll take the product, and we'll take the intersection, and if they are same, then they're independent. Which means the event A does not affect the event H, or just knowing P of A, we're not getting any new idea for P of H given A. Okay, so now we'll go to second discussion question. Here, actually here we're only drawing once, so we're drawing twice in this example. We draw one card, and then without putting it back, we draw a second card. So first Q is the event that you get a queen in the first draw, and then D is the event that you get a diamond in the second draw. So how do we compute P of queen? Number of queen, okay. Number of total cards. So that's easy. The second part is probability of getting diamond, and this is second draw. Okay, so the words I heard here are number of diamonds, remaining number of cards. Do we need to know what happened in the first draw? Yes. Because if we got diamond of queen in the first draw, then we're not getting diamond in the second draw. So that will affect. If we did not get diamond in the first draw, then the number of diamonds in the second draw is different. So to compute P of Q and D, what else do we need now? So we need to start thinking about what the events are, right? What are the possible ways you can get queen and a diamond where queen is in the first draw and diamond is in the second draw? Because you could probably get queen of diamond, then you get queen and then of diamond and then diamond in the second draw. Or you could get queen that is not a diamond, so other suits, and then diamond. And then you have to start computing that event. So one straightforward way would be just to write all the possible events and also all possible events when you draw two cards in a row, and then just use cardinality or counting the frequency. There could be other ways too, but we'll talk about that when we actually work on the problem set. So if we know the joint, this intersection probability, if we knew the marginal P of D and P of Q, can we compute P of D conditional Q? Okay. Okay. So we left on talking about independence, intersection of two events, and then we also talked about few things, like if two events are disjoint, then the sum of the probability is probability of the sum, right? Those were in the laws of total probability. So we'll generalize that for more events or a bigger sample set. And actually, we'll talk about partitioning a set into different parts that are disjoint. And then if we were to take, interested in taking probability of B, and then we have these n different events that are disjoint and they partition, so they split the event B into different parts that are disjoint, then we can write probability of B, which is the marginal probability, as the sum of intersection of these n different probabilities. So this is the probability or law of total probability. And here, what I mean by this is if I had 1, 2, 3, 4, 5 different events, let's say A1 to A5, that divide this event B into 5 disjoint parts, so they don't overlap. For example, here there's this, and then they're all. Okay. Yeah, there we go. Then the probability of getting B could also just be written as sum of A1 and B, A2 and B, up to AN and B. And then we can start thinking about writing that joint distribution as conditional distribution times the marginal of each of those events. And we can finally write it as a sum. So this, again, is the law of total probability. So when we think about it in graphically, it makes more sense. You're just splitting this event into different disjoint size, and then we know A1 and B, A2 and B, which is each of area of each of those smaller conical thing. And if you add it up, you can get the probability of B. And these concepts are used quite a lot in probability and also in statistics. So when we think about Bayes' rule, actually, I wanted to see a raise of hands just to know how many people know about Bayes' rule in this class, or Bayes' theorem. Oh, quite a few. Good. So this is very widely used formula in statistics, and it also this whole idea of Bayesian statistics is built on this theorem, right? So the idea is if I wanted to get P of probability of A conditional on B, and I know P of B conditional on A and P of A, then I can actually get this conditional probability just by knowing this. So there are three parts. This is usually called the posterior of A, so AI conditional on B. And the first is the intersection. So we can write the formula for conditional probability to get this part. So this is P of AI intersection B, which can then be written as this product over P of B. And the denominator here is what we just learned using law of total probability, right? In total probability theorem, we said if there were n disjoint events that partition B, then P of B can just be written as sum of these n events. So knowing P of AI, which is usually called prior, and then the P of B of probability of B conditional on AI allows us to know P of AI conditional on B. And this is a very powerful formula, and I'll show some examples of why it's being used so often in statistics and probability. And there was one question in this problem set that you earlier solved that could have been solved using this formula, number 4. So I introduced this problem when I was talking about motivation, right? So we talked about prevalence of diabetes in Nepal, how likely it is. So that means probability of getting a diabetes is 0.25. And then we are also interested in diabetes in men. So we know that there are 100,000 people with diabetes. We know total number of men in the city and the total population. So what this gives us is a couple of different probabilities. We can then see the proportion of men in that town, which is number of men we have over total population, right? And then we also know the probability of diabetes conditional that you're a man. Is there any question? So then if I meet a random person with diabetes, how can I compute probability of that random person is a man given that they are diabetes? This is just the Bayes rule. We have the first part, I know diabetes given you're a man, the probability of men, and then the overall probability of getting diabetes in that area. Okay, so before I start talking about another part of this lecture, I want to go through some of the solutions. And I'll work on number 1 and 3. 1 and 2 are very similar. 3 is a little bit interesting. And people had some questions about that too. Actually, if someone wants to come and work it out, we can do that too. Is anyone interested in working on number 1? A lot of you have already solved it, so.
So the rest of today's class is going to be very interactive.
Yeah.
So if nobody volunteers, we will choose a random person from a random row at some point.
With some probability.
Yes.
So I can start for number 1 because it's simple, and then 2 gets more complicated, so then I'll ask someone to work on that. Can you see if I write here from the behind? So there are 3 marbles, red, green, and blue. And what we're doing here is we get 1 marble, and then we put it back, and then pick another one too. So what is the sample space? Sample space is different colors you'll get while doing this experiment, right? What can you get from this sample space? You can get red and red, red and green, and red and blue if the first one was red. Or you can get green and red, green and blue, and green and green, and blue and red, blue and green, and blue and blue. So what is the probability of getting one of these events then, if each of these is equally likely? 1/9. Okay. In the second question, you're drawing 1 marble, but you're not replacing it. So now, number of possible events are going to be smaller because you don't replace it. I would like someone to come and write the sample space for the second one. Come on. Do you want to work on it? Yeah, don't be shy. So it reduces to 6 possible events, right? Because you can get red and red, you can get green or green, or you can get blue or blue. So now the probability of getting each one of these events is 1/6. Thank you. Oh, so yeah, every time you come here, you'll get a clap. Now we'll work on number 3. And I can start with writing sample space, but then I'd like someone to come and work on the probability of 4 tosses. So here the idea is you toss a coin until you get 2 heads in a row. which means there's a lot of ways you can do it, right? If you get head and head, this is one event in your sample space. You can get tail and then head and head, or you can get tail, tail, head, and head. So you toss the coin until you get 2 heads in a row, and then you stop. Which means and then any other possible ways where you'll stop after getting 2 heads in a row. So now what we want is probability of that it will be tossed exactly 4 times, which means a coin is tossed 4 times, and then you're getting 2 heads in a row. So this is not the event we're interested in. This is not the event we're interested in, but this is, right? And this is. So can someone come and just compute these 2 probabilities? And we know that each face is equally likely, so probability of tail is 0.5 or 1/2. Or if you have questions, you can ask as well.